this talk is about some of the FM mini-apps. I will start with a general overview of each, and then I will go into deeper topics, research topics that were explored during using these mini-apps. I will go over many topics quickly. It won't be very deep in each. That's how the talk will be. But if you see something that's interesting and you want to discuss, talk to me after the talk or tomorrow. So the first one is Lagos. That was mentioned already several times. Lagos is a shock hydro mini-app using Modular Finite Elements to solve all the equations in Lagrangian frame. You see the mesh moves. Some bullets here. The main idea is that Lagos has been around for a while. It has been used to do accurate, robust simulations of shock hydro, and also for performance purposes, it has been one of the procurement mini-apps for El Capitan. It has been used in the ECP project for benchmarking. You saw some of the previous talks and so on. So the first topic we looked at was boundary conditions. We wanted to be able to run in more complicated curve domains. So for that, you see the top here. If you just set v equals 0 on the boundary, you see that it slows down on the boundary. Just this is incorrect. You see the velocity is 0 on the boundary. If you do the property, so slip wall boundary condition, the flow must go around. So the cell should be deforming like this here. Curve backwards is fall forward, so on. You see a very different proportion. You see the velocity moves correctly, mostly. No, more accurately. So how was this done? It was a weak enforcement. So there are two new terms, one controlling the normal velocity VO10 and the other one controlling the normal acceleration going into the mass matrix. This was derived by Nabil. He was a postdoc here. He spent a lot of time on this. And there are many tricks here, correct units. There is this trace inequality that enters into the formulation. It makes sense to be able to control quantities on the boundaries by quantities from inside the domain and so on. It must maintain magnitude under refinement, tricks like that. Then it propagates in the internal energy to have the correct conservation. The mass matrices are still constant in time, and we have the original conservation properties, the conservation properties of the original method. Of course, all details are in this paper here. This just shows that when you do that, you get the same results on the standard problem. Take order convergence, same in shock positions. And then in the paper, we did many tests, 2D, 3D with complicated shapes. You see, we let this is a Q3 simulation. We let it go when we have some clearly inverted elements here, but it can still keep going as long as you don't invert the curvature points you use.
Quick question.
Yes.
What's the initial mesh of that simulation? Double simulation with this?
The initial mesh is the same. It is where it hasn't propagated.
Oh.
Yeah, the blast wave starts from here. The initial mesh is like this everywhere, and there it goes. Yes. All right. Then our ultimate goal for this was shifted boundary conditions. These shifted methods is something that is very useful when you have all the finite elements in curve boundaries, because doing geometric operations becomes mostly impossible. So you need some kind of approximation in shifted methods. The idea of shifted methods is that if this is the true boundary, this white circle here, you don't enforce the boundary condition on the circle, but you enforce it on surrogate faces, on the blue face. And then instead of V.10 equals 0, you enforce V plus some Taylor expansion to take into account the difference in the position equal to 0. So it's an approximation. But even if you do it exactly with low boundary condition, it's still weak. So it makes sense to replace one approximation by another if it gives you so many benefits you don't have to mesh and so on. And you see, this is a small example of a propagating wave. This is simulated on the full mesh. Nothing is done with respect to meshing. It just sees this feature by enforcing such things. Then we looked at interfaces, shifted methods for interfaces, same idea. You have a curved interface inside a curved cell. You don't want to do any geometry for that. If you can do integral on the face and do some variational thing, that gives you a big benefit. So it all goes, the complication goes in the weak form. You see this, you want to enforce in this case that the pressure equilibrates on the interface and the velocity zero, and then you get these jumps with Taylor expansions and so on. There is a distance solver. You need the distance from your face to the interface. That's again finite element solve, things like that. So for this, we have another paper. You can take a look, some results. This just shows that for a smooth problem, you get the expected convergence rates. Basically, it's limited by the order of the Taylor expansion. Then you see the triple point with non-white interface. It can in the simulation, all these terms are active. They do something so that the simulation actually sees the discontinuous interface inside the cell. The last topic for Lagos we've been looking at in the similar spirit of embedded methods. We've been looking at cut integration. So again, you have something like this. A level set, zero level set cutting through the mesh. Can we integrate exactly? There are two approaches in MFEM currently. The first one was implemented by Jean-Philippe, who spent the summer here. He's a PhD student in Dortmund. It's moment-based. The idea is that you use the same quadrature rule. So even though you have some cut, you put same quadrature point, same positions, and then there is a linear solve to fit something like basis functions to integrate them exactly, and that gives you the weights. It gives you some weird weights, but with these weights you actually integrate exactly. And this is both native MFEM. You can see the example with 38. The other approach, Algoim, that's an external package. It does not do the same thing. It actually puts the quadrature points only inside the domains that it tries to integrate, and it also integrates surfaces, so it puts them on the surface. And there is a pull request right now that was mostly work with Jan Mazarov. Also, Ketan spent some time on that in the past. So yes, the idea is our goal is to take this, have a two material simulation in Lagos, and see if we can actually do exact integration. The main benefit will be that with the observation, right? With the shifted methods, there is always observation error from the shifting. All right, so moving to Remus. Remus is pure remap miniapp. It's based on pseudo-time advection. So we have two meshes, solution on the first mesh, and you want to move the solution. And this is, you can define a PDE to do that. Some requirements: you must conserve mass, you must conserve local bounds, it must be accurate. Again, order finite elements, no geometry, and so on. This is one of the papers. Actually, there are many methods in Remus that were based on 3 or 4 papers. Were written throughout the years about Remap. The first thing we looked about Remus, this was brought up by the application code, is that volume fractions, when you have something that is a jump function 0, 1, and you move that, with finite elements, you always get some propagation on the walk scale. So if you don't look at the walk scale, you see this, you say, okay, this is quite sharp, right? For zone diffusion. But if you turn on the walk scale, you see that actually it's many zones. Every finite element solve has the potential to move into the next zone. So when you have many time steps, even the values are small, they propagate. And when you have special materials, like the ones in the application code, and they propagate like that everywhere, that might be a problem. It is a problem. FGT does not help with that. The higher order solution also sees that. So you need to do something on the PDE level. what we did, we modified the material velocity. There are two ways to fill this diffusion. One is changing the convective term, as we do, and that has the benefit that you don't change your operator. So if you have things like partial assembly GPUs, if you only change the velocity, that changes nothing. That just changes the value of the conversion points. The other way is anti-diffusive terms. We don't do that. Some people do, most people do. Anyway, the idea is that you look at the velocity flow, the gradient of your indicator, and you change the velocity so that the material moves differently in that diffused region, so it sharpens itself. Some results on the log scale. If you don't do anything, you get this. If you do something with sharpening, you get this. You can see the difference in, this is just a look from above to see the difference in propagation. And some 2D results, same idea. Okay, this was mentioned by Paul. We looked at advection of H1 continuous fields. Remus is only doing L2 in principle, but H1 is important because in AO phase, if you do a longer AO, meaning you let the Lagrangian phase run longer, and then you want to do a bigger remap, so bigger difference between the meshes. And if you remap an H1 field like the velocity, and if that is not stable, you destroy your velocity, and then simulation is no good. That's why the application code usually does small remaps, actually. But Paul looked at that. Another student of Kuzmin, Paul is in Dortmund. He looked at stabilized H1 advection based on this MCL convex limiting by Dmitry. So you have two things. The D is like a diffusion. Point A is 0, you get the low order diffused solution like this. When A is 1, you get the high order, and then you blend them somehow to get a good solution. And you see what kind of difference we are talking about in the velocity remapping, something like Serov. This is one remap from this is run all the way Lagrangian, and then just one remap to the original mesh. Yes, there is a pull request by Paul under review. This is added to example 9 and 9p. And it will go into realms at some point. Yes, another project that is just starting is related to Remus is we want to do a completely different track, completely different approach for Remap. We want to look at the multi-material, full multi-material system, so not just a scalar field, but multiple materials, volume fractions, density, energy, and so on, and try to get all the properties we want, which is currently mostly impossible with the advection-based approach. So all these 4 properties, sharpness, conservation of all things we want, bounds, and consistent coupling between materials. And we want to do it through optimization. So we're looking at GSLib to make sharp initial guess through direct interpolation. Then 2 approaches for optimization, interior point methods with IOP, Kuzmin's library. And we'll also look at proximal point methods by Brendan Keith and his collaborators at Brown. Okay, moving to mesh optimization. Mesh optimization is something that we developed in the Ethos project. Ethos is a DOE project. We started with node movement. We just wanted to optimize meshes with node movement. This is the so-called TMOP approach. So you define what your elements want to be, and then you choose something that's called a metric that measures the difference between your current element and what you want to get. And you optimize this Newton solver or some other nonlinear solver, and it moves the nodes it solves for X, and you get the optimized mesh. Then we, in the mesh optimization Miniapp, we move to productivity. So we base this approach on the discrete fields that you have in your simulation. And then we move to other things with like optimizing meshes through edge adaptivity. For example, having more elements in non-smooth regions and less in the smooth regions. And then same idea with P adaptivity. So more higher degree in smooth regions and the opposite in non smooth. And this is mostly driven by Keaton's work on Ritus. You can see some papers here. We have many papers. This project has been going for a long time. The latest thing we were looking at surface fitting. The idea of surface fitting is you have a discrete function, a level set function with a zero level set that gives you some positions, and you want to take some of the mesh nodes and put them exactly at these positions. This is the basic idea here. This is the formulation. This term enters, which again makes it all variational, no geometry. For boundaries, there are things like background meshes to represent your level set with AMR. You can see some examples here. Complicated. This is all fitted without any geometric operations. And Keaton has been putting this on the GPU. There is a pull request with his sound students that is under review, I believe. The paper is here. Another thing, this was related to the boundary conditions I started with. If you want to do an AO thing, you need this tangential relaxation also during mesh optimization. We do it exactly in the sense that we eliminate some the degrees of freedom on the boundary. We change the representation through the parametrization so that it moves correctly, then it moves to the derivatives. One thing here is that usually your degrees of freedom don't start exactly on the curve. That happens because in the Lagrangian phase it was approximately, it was weakly. So if you don't start on the curve, you need to be careful how you move, how to be robust, and so on. There are details here. It will be published soon probably. And this is just an example. If we start with this mesh, you want to keep this curve here. Of course, if you optimize not all the way, you get something like this. If you optimize all the way, you get this. This is just the idea to move these nodes while you keep the curve, again, without any geometry. And finally, this is something we wanted to look at in relation to AD work, differentiation work in FM. So the question is, if you have a mesh, you optimize, you get good quality, but how do you know that actually helps you for your PDE solution? So if you ask the question, what's the best mesh for a given PDE, given initial conditions, so that I'll get actually the best approximation at the end on this mesh, then you need to go both ways because, the PDE depends on the mesh depends on the PDE. So we have Matthias Schmidt working on that with shape optimization tricks. And he actually got some good results. So this enters the functional. This U is actually a solution of a dot plus equation in this case, and U star is the exact solution. So you put this in the mesh optimization, and if you solve on these uniform or random meshes, you get these errors. If you optimize your mesh so that it fits the solution of the PDE best, you get much better errors. This is very preliminary, but it's looking good so far. All right, so the summary just repeats what I went over. So for shock hydro, all boundary conditions and curve domains, shifted methods, exact fit integration. In Remos, the Remap Miniapp, we have the sharpening, we have stabilized H1, and we're looking at optimization-based approaches. And for mesh optimization, just RHP adaptivity at this point, we can do all this for the mesh. Surface fitting, tangential relaxation, and PDE-driven adaptivity. So that was it. Yes, the goal of this talk was to go quickly over these Miniapps, show you the latest developments, and also show you ways in which you can take this and do interesting research problems of your own. Thank you.
Thank you, Vladimir.